potential due to a system of two charges. 1 by 4 pi epsilon 0 q1 q2 by r12, where r12 is the distance between the two charges. Okay. See, you have to work hard every day's portion. We must find time to complete that. That way you have to study. Today we are going to study the behavior of a conductor in an electric field. Okay, I will show you a video. Okay, I will explain with the figure first. Okay, children. Behavior of a conductor in an electric field. Children, how will you produce an electric field? Please tell anyone. How will you produce an electric field? Electric field? Anyone? See, we need two plates. Uniform electric field, I am telling. One plate you give positive charge, other plate you give negative charge. Children. So, take two metallic plates. One plate you give positive charge and other plate you give negative charge. Then, in between that, according to Gauss's law, we have said there is a uniform field. We have calculated the field between two plates. Who is waiting? Abarna. Okay. So, how will you produce an electric field? Please respond, children. We need two metallic plates. One plate, if it is plus sigma, other plate is minus sigma. Between that, there will be an electric field, and these pink lines represent the electric field line. So, how will you produce an electric field? Adityan? Adityan, orangana? Adityan? ഉറങ്ങായിരിക്കും കുറെ പാരൻസ് തന്നെ പറയുന്നുണ്ട് കുറെ പേര് ഓൺ ചെയ്ത് വെച്ച് കിടന്ന് ഉറങ്ങാന്ന്. അഭിനവ്, how will you produce an electric field, uniform electric field? എല്ലാവരും ഉറക്കാണ്. ദീപാങ്ഷ, how will you produce a uniform electric field? How will you produce a uniform electric field? How will you produce a uniform electric? You don't know, I just told now. Just now I told. Take two metallic plates. Are you not hearing? Break. അതാണ് പ്രശ്നം. ജ്ഞാനപ്രകാശം?
Yes, ma'am.
How will you produce a uniform electric field?
By keeping two of uniformly charged.
Opposite.
Uniformly distributed
charge. Opposite. One plus sigma surface charge density, other minus sigma surface charge density. Understand? Then in between that there will be an electric field E equal to sigma by epsilon 0 that we have studied in Gauss's law application. We have studied electric field between the two plates. Electric field between the two plates of two metallic plates. One plus sigma equal and opposite charge. Then only we get a uniform field sigma by epsilon 0. What is the electric field, children? What is the magnitude? Equal to sigma by epsilon 0. So that is most important thing. How to produce a uniform electric field. In capacitor also we need that. So one plate is plus sigma, other plate is minus sigma, then it produces a uniform electric field and the value of the electric field is sigma by epsilon 0. Okay, children? Now we are having an electric field and what we are going to study? Behavior of a conductor in an electric field. So conductor, what's a conductor, children? What's a conductor? Conductor. Akshaya, what is a conductor?
Yes, teacher. Materials which allows the current to pass through them.
Material which allow the current to pass through them. That is a conductor. So, conductor and insulator, why conductors allow the electricity or heat to pass through them?
They have excess number of electrons.
No, free electrons are available.
Free electrons.
Free. You have to use that word, free electrons.
Okay.
So, electrons are there in both, but free electrons. In insulator, bound electrons are there. So, not easy to release them. But here, free electrons are available in conductors. So, inside the conductor, there are free electrons. So, such a conductor is kept inside a uniform electric field. We know one plate is positive, other plate is negative. So, what will happen to the electrons in the conductor? Which direction they will begin to move? They are free. So, which direction they begin to move? Positive plate or negative plate? Electrons in this conductor, children? I'll ask to Adilakshmi, which direction electrons move? Towards the positive plate or towards the negative plate? Electrons in the conductor?
Positive.
Towards the positive plate. Correct answer. Electrons will move towards the positive plate. You see, electrons all will come and arrange near to the positive plate. And when all the electrons from the right side move towards this left side, what will be the charge of the right side of the conductor? Electrons are moved to the left side. So what will be the charge?
Positive.
Equal amount of positive charge. One electron is gone, one positive charge. Two electrons are gone, two positive charge. So this end, you can see near to the negative plate, conductor become positive, and near to the this positive plate, the conductor becomes negative. Clear, children? When a conductor is kept in a uniform electric field, rearrangement of electrons charges take place. Electrons come and arrange near to the positive plate and equal number of positive charge it get where on the right side of the conductor. Okay. Now we can see here externally what is the direction of electric field? Positive to negative or negative to positive? What is the direction of electric field? What is the direction of electric field? Electric field and all we have studied.
Positive to negative.
Positive to negative. That is the direction of. So externally you can see plus sigma, that plate to minus sigma plate. Positive to negative. That is the arrow mark is also showing that direction of electric field. And here inside the dielectric also, electric field direction is positive to negative. So external electric field, we denote it by E0. External electric field is towards right, but inside the conductor, what is the direction? Left or right, children? Inside the direction? Towards left. This is positive, this is negative. So there will be an electric field, for example, EP. Suppose we are taking a EP. the electric field EP. Inside the dielectric, there is an electric field EP, which is opposite to the direction of the applied electric field, external electric field. So, externally, it is from left to right, and internally, it is right to left, opposite direction. And you know, until what time this rearrangement of charges or flow of electron take place? Do you know? Until what time will it continue forever, or will it stop after some time? What is the condition? See, when external electric field becomes equal to the internal electric field, the flow of charges become or stops. External electric field becomes internal electric field equal. Then the flow of charge stops. And also we can see when all the electrons are arranged here, further the electrons cannot reach here. See, all the electrons are arranged, and another electron from this side cannot come here because they will repel. So it attains a static state, static situation. Interior of the conductor, and when it attains a static situation, don't think that there are excess charges. There is no excess charge. Electrons come and arrange here, positive charges are here. No excess charge it got from anywhere. So interior of the conductor can have no excess charge, only the rearrangement of charges only has taken place, and it attained a static situation when external electric field becomes equal and opposite to the internal electric field. Internal electric field becomes equal and opposite to external electric field. It attains a static situation. And you know, then inside the conductor, electric field is zero. Inside, here see, charges reside only on the surface. Inside the conductor, electric field is zero. That is a very important property. So all the charges come and arrange near to the surface. Negative charges here, positive charges on the surface, not inside, on the surface. And inside, electric field becomes zero because E0 equal to EP. So E0 minus EP will become zero inside. Inside, the electric field becomes zero. That's a very important property when a conductor is kept in a uniform electric field. Okay, there is no excess charge. When it attains a static situation, there is no excess charge, second property. Then, next one, electric field just outside. A charged conductor is perpendicular to the surface of the conductor at every point. Electric field just outside, that means here, this electric field outside the conductor. This electric field is perpendicular to the surface of the conductor. See, how will you prove it is perpendicular? How will you prove it is perpendicular? If there is a, suppose instead of drawing perpendicular, suppose we are drawing it inclined at an angle. And then it will have two components, one component along this, other component perpendicular to that. Two components it will have. And if there is a component along the surface of the conductor, if there is a component of electric field along the surface of the conductor, what will happen to the charges? Charges will move. Electrons will move opposite to the direction of the field. Electrons will move opposite to the direction of the field. But we are not seeing any motion of electrons on the surface of the conductor. That means there is no such component of electric field on the surface of the conductor. The electric field is always normal to the surface of the conductor. Sometimes even though it is a property, you will get question like that. Show that electric field is perpendicular to the surface of the conductor. How will you show? First we are taking electric field is not normal. That's it. Such situation we consider. Consider electric field is not normal. Then we tell, then it will have two components. One component along the surface, one component perpendicular to that. Then if there is a component along the surface, component of electric field along the surface, electrons should have moved opposite to that direction, or charges would have moved, positive charges would have moved along the direction of the electric field. but we are not seeing any motion of charges on the surface of the conductor. That means there is no such component of electric field along the surface of the conductor. Then what is possible? The only possibility is the electric field is normal to the surface. Okay, that is the explanation for that. Even though it is a property, you have to study the explanation. Electrostatic potential is constant throughout the volume of the conductor. Electrostatic potential is constant, another important property. Potential is constant throughout the volume of the conductor and has the same value on its surface. Potential is constant. Electric field is normal to the surface. Charges reside only on the surface of the conductor. Net electric field inside the conductor is zero. In static situation, there is no excess charge. All are very, very important properties. Next, potential. What about the potential? Electric field, we know it is normal. Electric field outside sigma by epsilon 0. Electric field inside 0. All such things we have seen. Then, what is potential? Potential, we have studied one relation E equal to minus dV by dr. When E equal to 0, inside the conductor E equal to 0. So 0 equal to dV by dr. We can write 0 equal to dV by dr. 0 equal to minus dV by dr. We have already studied derivative of a constant is 0. Isn't it, children? Derivative of a constant is 0. So that means V is a constant. So inside the conductor, throughout the volume, not only inside, on the surface also, the potential is constant. Now work is done to move the charge on the surface of the conductor. So what we have seen? Inside the conductor, electric field is 0. What is the potential, children? Is it 0? Potential is constant, says like that. Potential is constant. Okay? Constant potential, same potential, Q potential like that. Same potential you can see. Throughout the volume of the conductor, volume is constant, children. Then next, electric field at the surface of a charged conductor is vector E equal to sigma by epsilon 0 into n cap, where sigma is the surface charge density and n cap is the unit vector normal to the surface in outward direction. Electric field at the surface of a charged conductor. Electric field, I told you, electric field is only there on the surface of the conductor, and its magnitude is sigma by epsilon 0 into n cap as a vector quantity. Sigma by epsilon 0 into n cap. So electric field at the surface of the charged conductor is sigma by epsilon 0 into n cap, where sigma is the surface charge density, n cap is a unit vector normal to the surface in outward direction. Okay, see. So what all properties we have studied, children? Everybody should know what all properties. Inside the conductor, electric field is 0. Why is it 0, children? Why is it 0? Externally, there is electric field is 0. In that electric field, the conductor is kept. So the electrons move towards the positive plate and equal number of positive charge it get on the right side. So due to that, an electric field is set up inside the conductor and the charge flow takes place until both the fields becomes equal and opposite. When EP becomes equal to E0, then only the flow of charge carrier stops. That is static situation. In static situation, the conductor can have no excess charge. Okay, same charge, but they rearrange here. So then electric field just outside the conductor is perpendicular. How will you show perpendicular? If there is a component, we are contradicting that. We take there is an electric field inclined at an angle. From that we begin to prove that. We consider there is an electric field inclined at an angle. If there is such an electric field inclined to the surface, it will have two components. One component perpendicular and one component along the surface. And if there is a component along the surface, charges would have flown in that direction. positive charge will move in the direction of electric field. Electrons will move opposite to the direction of electric field. But we are not seeing any motion of charges on the surface of the conductor, which proves that there is no such component of electric field along the surface. So only the electric field is normal to the surface. And its value is sigma by epsilon zero outside. So inside, what is the I will ask question after this. No? Potential. What about potential, children? What is the potential inside and on the surface? What is the potential? Abarna?
Constant.
Potential is constant. Potential is throughout the volume of the conductor, the potential is constant. Okay. Then electric field just outside the surface of the conductor is sigma by epsilon zero. So some children is having net problem. Those children, and I put a video class on this, and I will send to you video, and you can listen to that. If anybody feel any difficulty to understand this. Yes.
It's a number of conductory properties effective.
Number of
conductors.
നമ്പർ ഓരോ കണ്ടക്ടറിലും അങ്ങനെയായിരിക്കും സംഭവിക്കുന്നത്. ഓരോ കണ്ടക്ടറിലും ഇതേ സംഭവം തന്നെയായിരിക്കും കേട്ടോ. ഓക്കെ. And we have to do some problem. One more thing, yes. Electrostatic shielding also is there. That is also a property of the conductor. So suppose there is a cavity inside the conductor. Suppose there is a cavity inside the conductor. For example, this is a conductor. It is kept in an electric field, and inside the cavity. Cavity means നമ്മൾ എന്താ പറയാ cavityക്ക്? Cavityക്ക് എന്താ പറയാ? ഒരു കണ്ടക്ടറിൻ്റെ ഉള്ളിൽ ഒരു കുഴി പോലെ ഉണ്ടെങ്കിൽ, മനസ്സിലായില്ലേ? കണ്ടക്ടറിൻ്റെ ഉള്ളിൽ ഒരു കുഴി പോലെ ഉണ്ടെങ്കിൽ, കാവിറ്റി ഉണ്ടെങ്കിൽ, inside the cavity electric field is zero and potential will be constant. Electric field is zero. Understand? That is a very important property. If when a conductor is placed in an electric field, inside the cavity the electric field is zero, and that principle is used in electrostatic shielding. Electrostatic shielding. What is shielding, children? What is meant by shielding? Shield.
Protecting.
Protecting. Yes, protecting. So electrostatic shielding means we can protect some instruments from electrical effect. For example, I will tell you, during the thunderstorm, thunder and lightning, you are asked to sit inside a car. Suppose you are traveling, and it is safe when you are inside the car. Why, children? During lightning, it is safe inside the car than outside, standing outside or standing under a tree. Than that, it is safe. We are sitting inside a car, because car's that body part is made of plastic ano? Metal. Body part is made of metal. So when we sit inside the car, when lightning comes, the charges will spread on the surface of the conductor. When lightning is an external electric field. When external electric field come, all the charges will reside on the surface of the car. It will not enter. That is a property of the conductor. And inside car can be considered as a cavity also. Inside the car, that is, we are sitting in a cavity. Metal inside we are sitting. So the charges reside only on the surface of the car, and we are safe. No electric field will enter into inside the car. All the charges will spread on the surface of the conductor, or that means car surface, or that body part only. Charges reside only on the body part of the car. Inside we are safe. So that you can Faraday cages are there. Faraday cage means just like a cage of cage of a bird. It is made of metal. തത്തമ്മേരെ കൂട് കണ്ടിട്ടില്ലേ? തത്തമ്മേരൊക്കെ കൂട് കണ്ടില്ലേ? മെറ്റൽ കൊണ്ട് ഉണ്ടാക്കിയിട്ടുള്ള തത്തമ്മ കൂട് കണ്ടിട്ടുണ്ടോ? അതുപോലെ അതുപോലത്തെ ഒരു കേജ് ഉണ്ടാക്കും. എന്നിട്ട് ഇൻസൈഡ് ദാറ്റ് സപ്പോസ് an electric some device, that device should not be affected by electric field. We have to protect that device from external electric field. So we use such cages. So inside the cage, it acts like a cavity. So whatever charge comes, charges reside only on the surface of the conductor, and inside it will be free of any external electric field. So that is Faraday cage. Our question also asked from this part. What is the principle of Faraday cage, or what is the use of Faraday cage? Faraday cages are used to keep electrical instruments which are to be protected from external electric field. So we keep the devices, we protect the devices from external electric field by keeping them in Faraday cages. In the Faraday cage inside, it acts as a cavity, and the electric field inside the cavity is zero. So that is explained here. That phenomenon is known as electrostatic shielding. Phenomenon of protecting a certain region of space from external electric field. We know the electric field inside the conductor is zero. Therefore, to protect delicate instruments from external electric field, we enclose them in hollow conductors. Such hollow conductors are called Faraday cages. Electric field inside cavity is zero. In a thunderstorm accompanied by lightning, it is safer to be inside a car or a bus than to be in the open ground or under a tree. And you have seen a figure. There is a cavity here. Inside the cavity, electric field is zero. Potential will be constant. And here externally there is, see, the positive charges are here, negative charges are here, and externally depending upon this there will be electric field. Positive charge ആണെങ്കിൽ sigma by epsilon 0 outwards ആയിരിക്കും. നെഗറ്റീവ് ചാർജ് ആണെങ്കിൽ സിഗ്മ ബൈ എപ്സിലോൺ 0 ഇൻവേർഡ്സ് ആയിരിക്കും. നെഗറ്റീവ് ചാർജ് ഇലക്ട്രിക് ഫീൽഡ് ഇൻവേർഡ്സ്, പോസിറ്റീവ് ചാർജ് ഇലക്ട്രിക് ഫീൽഡ് ഔട്ട്വേർഡ്സ്. ദാറ്റ് ഡിപ്പെൻഡ്സ് അപ്പോൺ that surface charge density, sigma by epsilon 0, or electric field, that depends on sigma. Here it is plus sigma, here it is minus sigma. So direction of electric field, minus part it will be inwards, plus part direction of electric field will be outwards. So many meanings are there when you draw a figure. Sigma greater than 0, positive. Sigma less than 0, negative. Electric field inwards, positive charges, electric field. So same body itself, it can have different values of electric field depending upon the surface charge density. But inside a cavity, inside a conductor, the electric field becomes zero. Okay. That is about the electrostatics of conductors. And let me ask question, whether you understood or not. That idea I will get only when I get the answer, children. So what are the properties of a conductor when it is kept in a uniform electric field? I'll ask question. First question, how will you produce a uniform electric field? Gautam, how will you produce a uniform electric field? Gautam is there? Gautam? Adityan? Adityan? Pavitra is there?
Yes, teacher.
How will you produce a uniform electric field?
That will keeping positive and negative charges.
Two plates. Take two plates, metallic plates. One is plus sigma, charged positively. Surface charge density plus sigma. Other plate is surface charge density minus sigma. And there is a separation between the two plates. If you keep like that, what will happen? There is a uniform electric field between the. What is the magnitude of the electric field?
Zero.
Huh?
Zero.
Not zero. 1
That
plus
is sigma by epsilon zero.
Sigma by epsilon zero. External electric field is sigma by epsilon zero. Sigma by epsilon zero. What is sigma?
Here, surface charge density.
Surface charge density, sigma. But first thing you should know that how to produce a uniform electric field. Next question. What is the difference between insulator and a conductor? What is the difference between insulator? Gramya is there? Gramya? Harunisa, what is the difference between insulator and conductor? Harunisa? Harunisa ഇല്ലേ പോയോ? അഭിനവ്? ഒക്കെ ഓൺ ചേർന്ന് ഉറങ്ങാൻ വന്നിട്ട് അക്ഷരം ഉണ്ടാവില്ല. Alok? Maharunisa, what is the difference between insulator and conductor?
Insulator, the current will flow.
Current will flow na insulator.
Alla.
Eh?
Conductor, current flow easily through it.
Conductor allow current flow. Le? Why conductor allow current flow? Why?
Because electric charge.
Free electrons are there because free electrons are available in conductors. Okay. So when such a conductor is kept in an electric field, what all behaviors? One property tell. Who will tell the property? Krishna Sri, one property tell. Krishna Sri. Krishna Sri poya. Aditya, tell one property when a conductor is kept in an electric field. Aditya. Aditya മിണ്ടല്ലേ. Mitra. ഇത്രയും നേരം പറഞ്ഞിട്ട് ഒരാളൊരക്ഷരം മിണ്ടണില്ല എന്ന് പറയുന്നത്. Mitra, tell one property when a conductor is kept in an electric field.
The field outside the conductor is perpendicular to its surface.
The electric field outside the conductor is perpendicular to the surface. Okay, that is one property. Then another property, Nana. Another property. Nana. ഇല്ല, ഇനി മിണ്ടാത്തവർ ഞാൻ അറ്റൻഡൻസ് ഇടില്ല കേട്ടാ. റിയ, അതായത് ഉറങ്ങണമെന്നതിൻ്റെ അർത്ഥം. നിങ്ങൾ അറിഞ്ഞൂടെങ്കിൽ അറിഞ്ഞൂടാന്ന് പറഞ്ഞൂടെ? റിയ ഇല്ല. ഋതു പറഞ്ഞ ഇല്ല. തമന്ന ബില്ലുരാജ്, തമന്ന ഷാജു, എല്ലാവരും വിളിച്ചില്ല കണ്ട. ദേവിക ഉണ്ടോ? ഒരെണ്ണം ഉണ്ടറില്ല. ദേവികയാണോ? Then tell one property.
Potential is
potential is constant. Where? Inside and also on the surface. Inside and also on the surface of the conductor, potential is constant. Okay. What about the electric field inside the conductor? Tamanna Billuraj. അറിയില്ല. നിവേദിത. Mitra, tell what is the electric field inside the conductor?
sigma by epsilon zero.
Electric field inside the conductor.
Zero.
Inside the conductor becomes 0. So when a conductor is kept in an electric field, Pranav, what happened to these electrons when a conductor is kept in an electric field? What happened to the electrons? Pranav. ഉണ്ടല്ല പ്രണവ്. Muhammad Adil, M.A. Muhammad Adil. When a conductor is kept in an electric field, what is happening to the charge carriers? M.A. Muhammad Adil. ഇല്ല. Muhammad Adil. അവനും മിണ്ടില്ല. ഒരെണ്ണം മിണ്ടില്ല. മനു ശങ്കർ. Adul Krishna. When a conductor is kept in an external electric field, electrons move towards the positive plate and equal number of positive charges are formed. And electrons in the place of the electron. An electron moved to negative plate, external electric field, negative plate, the external electric field. So, the electric field is produced inside EP, which is opposite to the external field. And it attains a static state when internal electric field is equal and opposite to the external electric field. Okay, children? Well, these are all the things happening inside the conductor. So I will send the video also. If you feel any difficulty, watch that also, children. And we have to do some problems on potential. Now, new one we cannot take. Shielding also very important. What is electrostatic shielding? I will ask that also. What is electrostatic shielding? Abhinav, can you tell what is electrostatic shielding? Abhinav? 33 ആളുണ്ട്. എല്ലാവരും അവിടെ ഇരുന്ന് ഉറങ്ങണം. ഒരക്ഷരം മിണ്ടറില്ല. സാഗർ, ശ്രീരാഗ്, ശ്രീരാഗ് മിണ്ടറില്ല. ആദിത്യ, വാട്ട് ഇസ് ഇലക്ട്രോസ്റ്റാറ്റിക് ഷീൽഡിംഗ്? ലക്ഷ്മിപ്രിയ, രക്ഷയില്ല. ജ്ഞാനപ്രകാശം പറഞ്ഞ വാട്ട് ഇസ് ഇലക്ട്രോസ്റ്റാറ്റിക് ഷീൽഡിംഗ്?
Yes, ma'am.
What is electrostatic shielding?
Ma'am,
Electrostatic shielding.
Electrostatic shielding. Okay, ma'am. It is a protecting shield around the protecting electrostatic shield.
Protecting what?
Protection to without protecting a body inside against
Protecting a device. External electric field. Protecting a device. For example, if some device damages due to external field, that device is to be protected from external field. So, you have to keep that in a cavity. Inside the cavity, electric field is 0. So, it is better to keep such instruments inside a cage, just like Faraday cages, to protect instruments from external electric field. That is Faraday cage. And that is why it says it is better to sit inside a car or a bus than standing outside or standing under a tree. It is better to sit inside a car or a bus at the time of lightning or thunderstorm, because lightning is an external electric field and we will be protected. We are sitting in the cavity of the bus, cavity of the conductor. So, external electric field will not affect us. So, that is known as a protecting device or the things. from external electric field. This property of the conductor is protecting us from the external electric field. So electric field inside a cavity is, complete the sentence children. Electric field inside a cavity is
0.
0, correct. Okay. So that is taken next. You can do this problem, one problem. Calculate the potential at the center of the square shown in figure. Here is a very important question. Calculate the potential at the center of the square. You can see charges are kept at the four corners of the square, and each charge will produce a potential here. And we have to add all the potential to find the total potential at the center. Calculate the potential at the center of the square. So different amounts of charges are kept at the corners. And for that you should know distance. This distance is given 1 meter, 1 meter, 1 meter, 1 meter. But if that is given, you can calculate the hypotenuse by Pythagoras theorem. BD square equal to DC square plus DC square. 1 square plus 1 square